Hello everybody, welcome to week 5 of quarter 3 for physics. This week we're going to be talking about light waves, and then we're going to go into mirrors as well, and we're going to continue with mirrors up until spring break. We are closing in on midterms as well, so please look through your grade, get things submitted. If you are missing anything, I will still give you partial points for getting them in. Alright, so starting with light. The definition of light for something that we have known about since we were little kids, it has a really difficult definition. It is energy, we know that, in the form of electric and magnetic fields, electromagnetic radiation. We've talked about this before, the electromagnetic spectrum, when we talked about radio waves. Electromagnetic radiation, which means it has alternating electric and magnetic fields. So we can't break apart with our eyes the look of a light wave, but if we could, what we would see is this alternating, electricity creates magnetism, magnetism creates electricity. So we have an electric field, and then it creates a magnetic field, and then an electric field, and then a magnetic field. That's what it would look like if we could actually see the light rays alternating through their different forms as the light passes from one place to another. Okay, light also acts as both a particle and a wave as it travels. Okay, so specifically, we'll get back to that, looking at the electromagnetic spectrum. We brought this up when we talked about radio waves. I switched it around so that over here would have the lowest wavelength, the shortest wavelength, and over here would have the longest, the largest wavelength. So it's the opposite direction. So over here are the radio waves. They had super long wavelengths. They were like 2 football fields long, some of them. Okay, and then as we move towards here, we end up with TV. This is where microwaves would be as well. Infrared rays, that would be heat. Here is our visible light spectrum. So over here by the longer wavelength is red, orange, yellow, green, blue, and purple. And then as we get smaller and smaller into our wavelength, we have the things with a lot more energy, our X-rays, our gamma rays, and so forth. All right, electromagnetic radiation, the only part of it that our eyes can see, visible light, is the ones with a wavelength of 400 to about 750 nanometers. Okay, a nanometer is 10 to the negative 9 meters. Okay, so if you're talking about it in meters, it would be so the wavelength of visible light that our eyes can pick up, our receptors are able to turn into signals so that we can actually see them, this many meters to this many meters. It is only this tiny little portion of the electromagnetic spectrum. Okay, that's all that our eyes can see. Light does not need a medium to travel through. That is why light travels in space, whereas sound cannot. Sound needs a medium, it needs molecules to vibrate to pass. Light does not. It can pass through empty space. And it behaves like both a particle and a wave. So when I say a particle, think of like a proton. So it behaves like a particle in that it can just go from one place to another. It does not need a medium. And it's affected by gravity. If you have a huge gravitational field, like a black hole, it will suck in light. It is still affected by gravity. But at other times, it behaves like a wave. It has a crest and trough. It has frequency and wavelength. And its big one, light transfers energy. All right, so sometimes light behaves like a particle, sometimes it behaves more like a wave. All right, here we go. Our actual equation for light. It is one that you have seen before. I'm going to write the old one up above it. Our wavelength times frequency gives us the speed, so V equals frequency times wavelength. This is how we have calculated the speed of a wave. Knowing the frequency and the wavelength, we can find the speed. All right, for light waves, it's a specific speed. It is the speed of light, 3 times 10 to the 8th. All things on here move at the speed of light. Light is no exception to that. The only thing that's different is the speed of light gets its own variable. It is a c. So c, when you're specifically talking about light waves, the velocity, it gets its own variable for the speed of light. It is a c. So c stands for the speed of light, which is 3 times 10 to the 8th meters per second. All right, so the speed of light is still the speed of light, 3 times 10 to the 8th meters per second, but now it just has its own variable. When you see the letter C, you know that you need to plug in 3 times 10 to the 8th. That is on your equation sheet in the waves and the light and mirrors area. Okay, and then the other side of the equation remains the same. F still stands for frequency, and that has to be in hertz. And the upside down Y, lambda, still stands for wavelength. And it's a length that still has to be in meters. So we always have to be in hertz and meters in order to use this equation. Okay, same as before, looking at this equation, frequency and wavelength, they are multiplied by each other on the same side of the equal sign. That means they have an inverse relationship. If one goes up, the other goes down, and vice versa. Okay, so as the wavelength of light increases, so if your wavelength goes up, your frequency will go down. It does the opposite. If you go back up to this electromagnetic spectrum, over on this side, over here by gamma rays, they have a very short wavelength. So they're tiny, tiny, tiny little waves. The distance of the wave is super, super small. Which means, because they're so small, many, many, many of them can come per second, so they have a high frequency. There's an inverse relationship. Over here on the other side, when we were looking at radio waves, they have a really long wavelength, so they are like 200 meters long, some of them. Okay, which means if that is how long it is and they all move at the speed of light, then not as many of them are going to happen in a course of a second. They have a decreased frequency. There's the longer the wavelength, the lower the frequency. All right, you guys cannot see the colors. I can't print in color. So what I did down here is purple, blue, green, yellow, orange, and red. You can go through and color over that document if you want to. Just so that you can see where the colors actually line up. In this visible light spectrum, purple is kind of in the 4 to 450 nanometer range. Then comes blue, which goes up to about 500. Green is right around 500. Yellow is kind of in that 550. Orange is about 600 nanometers. And then red is about 650 to 750 or so. Okay, you'll be using that diagram for one of our labs at home this week. Finishing off our notes, which color, green or red? So I'm only giving you two choices, green or red. Here's green, here's red. Which has a greater frequency, more waves per second, and you need to explain your answer. All right, so if we want to have a greater frequency, that means inverse relationship, we have to have a lower wavelength, Okay, so if we go back up to our diagram up here, the side that has a lower wavelength with a higher frequency is this side over here. So here's green, here's red. This has a smaller wavelength, which means it has a higher frequency. So green, because it has a smaller wavelength, which equals a higher frequency. Which color on the spectrum has the longest wavelength? Okay, long means bigger, larger number. Over here, we have 400. Over here, we have 700. 700 is bigger than 400, so a longer wavelength is going to be red. Which color on the spectrum has the highest frequency? frequency. Highest frequency. All right, well over here, higher frequency because they have smaller wavelengths. The lowest wavelength, the smallest wavelength, and then the highest frequency is on this side right here. That would be purple. And then finally, what else have we studied that moves at the speed of light? Thinking back just a couple of weeks, hopefully you remember radio waves. We're also going to look at microwaves this week in our take-home lab. All right, so that is the notes for light. It's not a lot of new information. It's the same equation you've been using. The only difference is this V is now a C because specifically not any speed can go in here, only the speed of light because we're working with light waves. All right, for your problem set, you have a few problems. Number 1, 2, 3, 4, those are kind of working through. You will need to use C equals the frequency times the wavelength, and you may need to use the V equals delta X over delta T. Light waves still move at a constant speed, so that equation is still valid right there. Number 1 is just a conversion. You're changing meters per second into miles per hour. You need a 2-step conversion to do that. Number 2, a light year is the distance light would travel in a year. Find the distance in meters of a light year. All right, so it says light moves at a constant speed, so we can assume V equals delta X over delta T. If we want the distance, that means we're solving for delta X. We know the velocity of light. It is 3 times 10 to the 8th meters per second. That's a given, okay? But we need to know the time, okay? For our time, it has to be in units that match up with this one right here. This is in meters per second. So our time has to be in seconds. Must have time in seconds. Okay, so we can assume there are 3 for our time. There are 365 days in a year. We're going to use that number. We are going to have to change that into seconds before we can plug it in for our time. Okay, you know how many hours are in a day, and you know how many seconds are in an hour. Okay, 2-step conversion, that will get you into seconds in a year. You'll then have the velocity of light times the seconds in a year. You multiply, that will give you your distance in delta X. From there, careful for bold. Just make sure if you see something in bold, it means you're going to have to convert it first. Okay, you're going to be another bold one right there. And then finally, when you look down to number 6, for my folks in class, they're going to actually head to a back lab station. In 9th grade, you guys use spectroscopes, in which you actually can look at light and it'll break it into its different colors, and it'll give you a wavelength associated with that. So they're going to go to the back lab station and look at a fluorescent light bulb in order to see that. For those of you at home, this website right here is going to show you this diagram. You can also just use this YouTube video to see the colors. Okay, so if you break apart, so what you're going to do is match the colors that you see here with the bands up here. And then you're just going to color over the top of them. So this one is kind of a bluey purple. This one is kind of a bluish green. This one's kind of a light green, a yellow, an orangey, and a red. So you're going to color over those, and then for each band, I have the wavelength listed there. For number 7, you're going to find the red band, and you're going to calculate the wavelength, or the frequency with the wavelength that is given. Okay, this website here has a whole bunch of these. This is what the spectroscope actually looks like in the inside of it. It was hard to find a diagram where they actually take pictures of the spectroscope. I could not get it to work with my camera, but this website does. So you are welcome to scroll through it and kind of see the difference between different types of light and different elements and things with your spectroscope. All right, the last thing for the first part of the week is our take-home lab. For this, you need to use a microwave. And it has to be non-rotating, which means it can't circle around. Most microwaves circle because it cooks it more evenly. So if yours spins, you just need to take out that glass piece that does the spinning and just take it out for this piece of the lab. If you don't have that option, or you don't have a microwave or anything like that, you are welcome to FaceTime or Zoom with somebody that does, or go to somebody else's house and do it with them. All right, so first thing you're gonna do, use a paper plate. That way you don't get dishes all dirty and you don't make a mess in your kitchen. Okay, on the bottom of the paper plate, you are gonna cover it with mini marshmallows. I say mini marshmallows because they cook quickly and it happens very fast, but anything that melts easily. Chocolate chips, Velveeta cheese, shredded cheese. I've even had some people use egg whites where they just use enough egg whites where they cover the bottom of the paper plate. So you gotta fully cover the bottom of the paper plate. You're then gonna throw it in the microwave without letting it rotate, and it's gonna cook. If it's marshmallows, I start with 10 seconds because those heat up pretty quickly. Other things need more like 20 to 30 seconds. So try 10 seconds, and if nothing's happening, then add another 10 and kind of go from there. Until you see some of the pieces of the food start to melt. Not everything will melt, just certain parts of it will melt. When you remove the plate, you'll see that it kind of lines up in lines. Okay, those lines have to do with the wavelength of the actual microwave that is cooking your food. You are going to measure the distance between the melted areas in centimeters. Okay, please be accurate. If it's 5 centimeters, put 5. If it's 5.5, 5.5. Okay, go to an accurate amount of centimeters for me. Okay, you then have to be in meters. So you have to divide by 100 to change your centimeters to meters. You have to be in meters for the calculations. For number 5, this distance in number 4 that you measure between your melty areas, just kind of go center to center of a melty area. That is equal to 1/2 of a wavelength. Okay, there's waves inside your microwave. It's sending out microwaves with wavelengths. Okay, that distance where it melts it does that every half a wavelength. So you're gonna take your distance in meters and you're gonna multiply it by 2 to get the full wavelength. That is the wavelength for your microwave. The other thing that you're going to need is the frequency of your microwave. A lot of them have a little sticker on the door or on the back of it that tells you the frequency of the microwave. If yours does not, use 2,450 megahertz. Need to convert that to regular hertz before we do our calculations. Just like FM radio, you need that 10 to the 6th. And then lastly, number 7, you are going to use this equation, C equals frequency times wavelength. You are going to calculate the speed of light based on the frequency and the wavelength of your microwave. Okay, so we are experimentally determining the speed of light. So you do not put 3 times 10 to the 8th in here. You're going to calculate it using the numbers from your microwave. That will be your experimental value. Okay, we know that the accepted value for the speed of light, we know what it should be, 3 times 10 to the 8th. Using the accepted and the experimental value, what you calculated it to be, you lastly are going to calculate a percent error for the speed of light calculation. So you're going to see how close you were able to get using your microwave to the actual speed of light. All right, that's the lab portion of it, and then I have one last light problem for you to do. If everybody were in class, we would look at spectroscopes and we would use them to break down different elements and to see their spectra, the different colors that make up that element. Mercury, you see 3 colored lines. I put the 3 frequencies in this chart. The first thing you're going to do is use your C equals frequency times wavelength. We know the speed of light. I'm giving you the frequency. You're going to calculate the wavelength in meters. Then, using the conversion factor, you're going to change the meters into nanometers, okay? And then finally, you are going to go back to your light notes. You are going to go to this diagram right here. These are the nanometers, 400, 500, 600, 700 of the different colors. You are going to match up whatever you get in nanometers. You're going to predict what color that should be for that specific line. All right, so those are going to be your 2 assignments kind of for the first half of the week. You have the back of the light notes to finish up the problems that go with it, and then you have the light lab as a take-home. Okay, later this week, you're going to be coming back here to learn about mirrors and the math behind them. So, thank you.